Good evening, teacher Julian Ernesto Moyapasa One. Today we will talk about our final report that it is called Optimization of Water Level Control in a Tank through a Cascade System. Well, I will continue this presentation with the authors of this report, like number 1, Mamani Gutierrez Roel Bernardo, number 2, Masco Montes Sergio René, number 3, Ruiz Reyes José David, number 4, González Carcausto Dalia Giuleni, number 5, Calderón Taki Edison, number 6, Huacayo Subizarreta Jorge Fernando, number 7, Ango Condori Uber Raúl, and the last one, Melentre Flores Brian. Well, after this we have the index with the topics of this report, like introduction, theoretical framework, background, objectives, problem statement, justification, tuning methods, development, analysis, diagrams, conclusions, and final. Well, then we have the introduction here. Well, it says that the report highlights the use of a cascade control system in mining for optimal water management. This system, using advanced technologies like sensors and regulating valves, synchronized level and flow control, ensuring operational stability and efficient water treatment. It sets a new standard in mining water management, promoting environmental sustainability. Then we have the background, where it says that the mining industry has struggled to efficiently manage water. Manual or semi-automated systems have led to impressive control. Cascade control systems, backed by technological advances and successful experiences in other industries, offer more precise water regulation and improving efficiency and reducing environmental impact.
Historical framework. Cascade control. It is characterized with primary and secondary control structure, where the primary control focuses on maintaining the level, while the secondary control regulation the flow. Erosion control. It refers the process of monitoring and regulation the quantity of input used in relation the product service generation. Next. Split range control. Control system was is single control variable, but two of more manipulation variables are sized as control. Override and feedback control. Control override are selects the most suitable control signal when control acts same variable. Feed forward control anticipates and compensates for the effect disturbance of process of input control. Select control analyzes the both signal from different control and select the highest or lowest signal since the actual. Level control to make constant level in the process water tank. Less trains will be sensed to provide precision measure of the water level. Flow control. Flow control wheels we carried out by science with pneumatic signals to regulation diaphragm operates valves. Signal integration. It considers the usage of electrical signal, software-based signal, and pneumatic signal to transmit information and ensure effective and precise communication among the control system components. Next. Objectives. General objective. develop a optimal cascade control structure ensure the stability of system I achieving effective performance. Specific objectives demonstrate all key in theoretical and laboratory class. The same process uses cascade control. Implement the design process in Studio 5000. Factory I/O and LabVIEW application. Apply Ziegler-Nichols tuning methods. Apply road hardware and body methods. Next. Problem statement. The mining industry needs efficient water management that further extraction and treatment of minerals. Accurate regulation of water level and flow is critical, but the lack of comprehensive control system has created operation chains. Difficulties. The lack of automated system has caused stability and water level and control variation in water flow. Effectivity that consists quality and efficiency of the treatment process in the mining industry. Next. Justification. The implementation of cascade control system justifies the adaptability, precision, and ability to handle specific challenges. Comparison with other types of control. Region control. Limits in evidence where simultaneous and proportional control of multiple variables is required. Cascade control is more adaptable. Split range control uses field-wide clear operation limits but can lead to stability. Cascade control others must contain regulation. Next. Comparison with other types of control. Selector control. Focus on choice between operation modes in as not optimal of continued and simultaneous adjustment. Cascade control allows gradual adjustments. Override and feed-forward control. Effectively and anticipate change or fail but mobilize acquires margin stability levels. Adaptability and precision of cascade control. It provides the necessary flexibility to simultaneously adjust and regulate the level and flow. Precision coordination between both parameters.
Software and method. Software LabVIEW. LabVIEW is a graphical programming platform using engine and automation. It allows users to design, simulate, and deploy complex control systems intuitively using graphical block called LabVIEW Graph. Point 1. LabVIEW offers robust graphical tools for implementing cascade control algorithms. Point 2. It facilitates the integration of specific and customized control models, allowing it to be adapted to different cascade control configurations. LabVIEW graphical interface allows you to quickly view and adjust system parameters in real time, making it easy to optimize the controller. Software Studio 5000. Studio 5000 is a runway automation platform for programming logic 5000 PLC used industrial applications to design control logic and configure complex systems. Advantages. Studio 4000 is used to accomplish programmable controllers in a cascade control extrusion. Facilitate the programming of control logic systems with control level that utilizes potentially. allows integration of measurements, device absorber, and the all elements necessary for the successful implementation of the standard control. Software Factory I/O. Factory I/O is an industrial simulation software that creates virtual environments of industrial processes. Its objective is to provide a platform to simulate a train control system, allowing users to experiment with industrial component virtuality. Key feature: process industrial simulation. Create virtual environments that emulate a manufacturing facility with machine and control system, intuitive and friendly interface. Offer a ways to use interface to interact with the plant elements. Real-time visual representation. Provide real-time visualization of industrial process. Test and learn. Allow you to test control configuration and use it as learning for industrial automation. Software Aerosmith Gateway. Aerosmith Gateway is a roadway automation software that facilitates communication between industrial automation systems as the bridge between roadway automation controller and other devices in application. Finish. The system enables real-time data transfer and seamless integration of control systems useful in industrial environments. It provides device functionality including alarm magnet, data monitoring, and secure communication via VPN. Software Studio 5000 Emulate. Studio 5000 Emulate in roadway automation software that simulate and emulate the operation of industrial automation controller, such as PLC and virtual environment. Bench. The software allows engineers and programmers to test and debug control programming with some physical access to the controllers, making it easy to identify and correct errors during the development and testing. User can learn and run con programs, monitor variables, simulate input and outputs, and perform extensive testing and ensure from operation of the control system before implementation. Communication OPS server. The OPS server is a software component that facilitates communication between systems in industrial automation. OPC, which starts off only for process control, is a widely used communication standard in industry. Bench. It is a server that provides access to data variables, allow application to access and write data in real time. It uses the OPC protocol for efficiency and reliable communication, allowing interoperability between device and the system for different manufacturers. Swing method, single loop code, machine code, open loop. The single loop code method applied an open loop system is the method that PID controller manually adjusts the products as type variation it is called.
Now I will continue the presentation where we have a sigmoidal signal. To use the Ziegler-Nichols method effectively, it is necessary that the system exhibit sigmoidal or shaped behavior. This means that the response must not have open-loop overshoots or integrative dynamics that steadily increase with the time. Where we have here the first method, where the parameters of the first-order system with delay can be obtained as follows. A tangent is drawn at the inflection point of the sigmoidal curve and the intersections of this tangent line with the time axis and the axis where c equals k. Here we have a board that presents this operation, where we have now the aeration curve open loop. If no gain is found that makes the system oscillates, then this second Ziegler-Nichols method cannot be applied. These oscillations are typical when the closed control loop presents higher order systems, like we have this graph. Then we have, once the oscillatory response is achieved with a constant amplitude, it tells us that the gain that achieves that response will be our limit gain, ultimate gain or critical gain, Ku. And from the graph we can calculate the critical period, Pu, which can also be calculated through the critical frequency as Pu equal to divided by P. Then we have this board. With these two parameters, we proceed to find the constants of our controller following PID, as just mentioned in the table here. P controller, PI controller, and PID controller. Then we have the development, understanding the problem. The issue focuses on the crucial need to maintain stable levels and precisely regulate the flow of processed water in the mining industry. The proposed solution is the implementation of a cascade control system to address these challenges and ensure optimal operation in the mineral treatment. Like we have this diagram, P and ID, that presents how we will solve this problem. Well, in this case, a cascade control is being used for the following reasons, like control provides superior stability, essential in mining. Then we have the secondary controller corrects disturbance before they affect the primary variable, acting as a control on the flow. Then we have the flow process towards the tank self compensates for any variation in the static gain of the secondary part, and the primary controller, with the help of the secondary one, achieved a great reduction in the variation of the primary variable, allowing harmonious tuning. Well, I will give the words to my classmate.
Okay. In this part of the PNID diagram, the internal cascade control loop is being indicated. In this loop number 1001, we have a flow controller that receives the signal from a flow transmitter. In turn, the leader is part of a flow sensor. Its process variable is provided by the sensor and its set point by the master controller, based on the signal's opening or closing the discharge valve. This flow controller is the secondary controller in the inter-cascade control. Next. Now we focus on the main loop, that is the primary controller. This is our level controller, which receives a signal from a level transmitter coming from a water tank. That signal it receives is compared with the set point, and we can modify this value. Being a master, this controller sends a signal to the slave and it takes it as its set point variable. According to this value, the internal loop of the secondary controller is established. Next. Well, here I show the behavior of the flow and the level in steady state. This it will help use later obtain the transfer function for the primary loop and the secondary loop of the cascade control. It can be seen that the flow curve, the green curve, for example, reaches the stable state in the less time compared to the control line, the blue curve. We have as a reference step the opening of the flow valve at the top of the tank. In the imagine, it is shown in color red and with an amplitude of 7. Next. Interpretation diagram of blocks. The blocks diagram of the cascade control is follows. We must start with tuning the internal loop where our secondary controller is chain of controlling the discharge valve is located. Then we tune the primary controller together to the secondary controller in charge of the controlling the discharge valve is located. In this part, the inner loop can respond quickly to changes in the secondary variable, minimizing unwanted effect on the primary variable. This makes the cascade control more efficient in the face of disturbance. Next. In this part, this is the level control SN factory IO. Here we have two flow sensors, a flow meter at the discharge and level sensor at the top. You can also see in initiation board with the start stop buttons or emergency buttons. This is the program under study 50,000 to start the auto cascade control. We lock the memory. Contact total pulse on the start button on the board. This will allow you just to continuously send signal to the slave and master PID blocks. Next. The response of the main variable of the process, which level to different disturbance and change in the set point variable can be seen. Responds monthly to any disturbance. Next. With respect to internal loop, in this part, it can be seen that it's very fast, which causes the slave set point to change very quickly, making the flow PV unable to completely follow the set point. Since the system already has speed, we are only using proportional control. My college, they will continue with the MATLAB tuning MATLAB tuning part of the entire block diagram. Explain it. Next.
Now we look at the graph. The factory IEO gives us about the secondary process. This begins faster than the primary process to be prepared for any alteration. Next. To find the mathematical modeling based on the graph, we export the data obtained in Factorio to Excel in order to have more precise data. As you can see in the image, we have the flow and our set point with a more precise time for the next calculation. Next. Now we will obtain the necessary parameters to fit the transfer function. From the graph obtained, we observe that our total gain is 4.93, step gain is 7, and the system gain is total gain or system gain, being 0.1704. Since our system has a delay, the value of the theta is equal to 0.03398, and the value of our tau, that is 63.2% of the total gain, is 18.78 seconds. After finding this data, we can obtain the following transfer function. Next. We can observe the data entered in MATLAB for the simulation where the set point is 7 and has a delay of 0.03398. Next. We will calculate for proportional control, since this way our system will be faster. Kp is equal to Kc. Kc is equal to 1 big 0.704, 18.78 over 0.03398. Kc equal is 785.054. Next. We use proportional control, since in this way our system will have a cyclic response in addition to helping to avoid effects at the same time it helps with disturbances. Next part. We observe our response to proportional control, checking that it reaches the set point faster without any oscillation. Next.
Okay, I continue with the application. Now, in this case, I talk about that my process is slow. This process is level. This process is the principal variable. We can see the graph. This graph is in Studio 5000. The graph, the answer, the system is very slower because the process is slower. Next. Okay. For the parameters of the transfer function is obtained from the Studios 5000. In this case, this graph is very similar with a comparison. The next graph is in MATLAB. Next, please. Okay, this is the open loop. In this case, the analysis, the transfer function is correct. Okay, in this case, the level for the level parameter is the gain. The system gain is in this case only of the system is 0.5432. Okay, the time is 36.97. This time is a little more in comparison with the process flow, okay, because this process level is slower. Now, and the delay is in this case 1.956. Okay, these parameters is interesting in the MATLAB, in the function transfer, in open loop. Next, please. Okay, this is the answer of the system. In this case, very similarly of the Studio 5000, and this is the answer in MATLAB. Okay, next. Now we continue with the tuning. In this case, use the primary controller tuning, the reaction curve method. This is the first method, the Seeger-Nichols. Okay, the proportional gain in this case for my control action is PID. Okay, the proportional gain is 71 that 5499472, and my integral gain is 31 that 4229017, and finally my derivative gain. Okay, in this case is 40 that 172988074. Okay, this analysis is in the control cascade because I including the secondary process. In this case is flow. Okay, this process is in open manual tuning. Okay, continue. Okay, this is the answer of the system. In this case, tuning is very good because the answer is the stability of the system is in approximately in 15 seconds. Okay, is very good answer, and the system is not present in this case oscillations. Okay, continue please. Okay, in this case we can use the perturbation in process level. The perturbation is in this case is very it's not affected the perturbation with the flow. Okay, it's not affected the principal variable, in this case is level. This is the control cascade, and the perturbation in the secondary in the principal variable, in this case in loop of level, is affected, no? But this case not occurred because the process is slower.
Okay, I will continue with the exhibition. Calculation. First, we will find the secondary control. We will be able to find the secondary driver. Deploying all of these, we will obtain a result that the following 0.704 over 18.78 is plus 1.74. Next. In the first, we will feed the secondary control. In the same way, we will dial back the time and level and flow. In the same way, it is double and the result is 0.3824 over 600
94.2966 is square root 81.17766 a is plus 2.0864. Siguiente, por favor. Next. Okay. To cut or any tuning method is the essential to have the complete transfer function of the system as does provide a comprehensive width of the stability of the system. Is consequently the calculation of the general transfer function was previously carried out, resulting in a second degree expression. This transfer function based on second degree provides us with crucial information about the poles and zeros on the system, which will later be used in the corresponding graph. This graphical representation of the poles and zeros is essential for understanding the dynamic behavior of the system and therefore facilitates the process of adjusting and tuning the control to achieve optimal performance. Again, next. Below we carry out the analysis by root Hurwitz. We will write the character equation. We create the first row of the root table. Initially we complete the coefficients in the evaluate correctly. It must be ordered and completed. Siguiente. Next. We complete the substring row in switch away, where you must multiply of 5 and divide in the following way for expressed in by. Next. Now we will evaluate our transfer function using the row curve criterion. The row curve analysis reveals that there are not six variables in the first column, which leads to the conclusion that our system is stable. This is important to keep at the stability of the system is associated with advanced option changes inside column. If any single change had been observed, it would have indicated the possibility of stability in the system. Next.
Now, we will evaluate by looking at some kind of stability range for your system. First, we see that the transfer function of the primary control loop is divided by one and the same function. We proceed to evaluate the possible stability in root Hurwitz, which when solved we can observe that k must be greater than less 5.4561. Then we proceed to evaluate the root location of the following transfer function. We're using MATLAB. We can observe that the system is stable since it is located in the right half plane. In addition, this behavior reaffirms the security and robustness of the system in the face of possible disturbance. Both analysis. This method has been used to determine the stability of the system. The general transfer function of cascade control has been obtained. Now, we proceed to present some case in which we could adapt the different types of control, such as override control, although this method is not so effective. It will help you anticipate certain change or failures situation. Below is the PNID diagram that has been proposed for this control system. In the lab view HME, we can see on the front panel a visual representation of the nested control that is being done, and in the block diagram we can see the connection so that your tank can operate in lab view, and we can see the level of the tank and the flow of the tannery. It is worth mentioning that the Studio 5000 program is being used for this, to link and work. Conclusions. The implementation of cascade control contributes to improving the stability of the industrial process by allowing more precise and faster control of critical variables. This results in greater consistency and reliability in production. Cascade control makes it easy to optimize operational efficiency by automating, coordinating, and adjust multiple process variables. This helps maintain ideal conditions and minimize resource wasted. By implementing cascade control, derivatives, and variability in the final product can be reduced. This is especially crucial in industrial production, where consistency is key to product quality. The ability to adapt to change in process conditions is a key advantage of cascade control. This ensures that the system can efficiently adjust to disturbance and change in demand without compromising product quality. By achieving great efficiency and stability, cascade control can contribute to reduce operating costs and ultimately improve industry profitability. Optimizing the use of recurse results in more profitable production. Thank you.